In this lesson, Gianna and I are going to try to show you how to derive the magnetic torque equation. To explain what we're looking at, we actually have two pictures here, and these two pictures are going to help us derive the equation. In the left-hand picture, we are looking at a coil of wire that would be placed on a rotating object that is placed in between a magnetic field. The right-hand picture is the same picture, but it's the bird's eye view in which we're looking down at the loop of wire. So we're looking at the two parts of the wire that are heading upward and downward. Now, before we start, what we need to recognize is that because the coil of wire is in a magnetic field, we must draw a magnetic field represented here in blue. And what we should hopefully recognize is that that magnetic field does cross through the current in a perpendicular way. And that will be important to recognize in just a few moments. All right, now we should also recognize that because there's a positive and negative side on this loop of wire, there will be a current that's going to spin, in this case in a clockwise fashion. And in the bird's eye view, it means that the current's going to be heading up at us, and then it's going to then head downward as it goes back the other way. Now, to do this, what we now need to recognize is that if we apply the right-hand rule on the bird's eye view, what we would see is that the dot that is pointing up has a current pointing up at us, so we would represent that with with our thumb, and with our index fingers, we would point to the right, indicating a force heading upward. Now, if we applied the same right-hand rule to the current that's heading down on the other side, it would push down. Now, in between these two forces, we actually have a pivot point. And that pivot point is really important because we have a force that is acting at a distance, which is going to be creating a torque, which will spin it in this clockwise direction. Now, if we go back over to the other picture, what we will recognize is that we have a width of wire and we have an area of length of wire traveling up and down. Now, if we go back to the bird's eye view, what we will recognize is that the lever arm in this case is actually half of the width of the wire, or of the loop. Now, to develop our torque equation, what we are going to recognize is that there are two torques that are being created here. So we're going to say torque 1 plus torque 2. Now, from old expressions, we should be aware that torque is a combination of force and lever arm, or in this case, force and distance. So we'll have Fd1 plus Fd2, keeping in mind that both distances are the same thing. The next step we need to recognize is that the force that's being used here is a magnetic force, so the F will become BIL. And the distance, or the lever arm in this case, is actually half the width, so we're going to replace D with 1/2 W. And the wire on the other side is of exactly the same length and of exactly the same lever arm, so it's actually exactly the same quantity. If we do a little bit of algebra here, we will recognize that the torque equals basically BIL W. Now, keeping in mind that length times width is area, then that length times width could be rewritten as BIA. So we have torque equals BIA. Now, on a motor, it's not very typical to just only use one loop of wire, so we typically use multiple loops of wire. So we are going to throw an N in front of this, indicating the number of loops that we use. And this is our torque equation for a loop that is in a magnetic